Not a fan of KC calculations? Well, let's have a go at this one together. So we've got a classic KC question here where you're given the starting moles or the initial moles of the reactant, and then you're given the equilibrium moles of a product. So I call this type of question an ICE question. So we're going to involve the initial moles, the change in moles, and the equilibrium moles of all the substances in the reaction. So there's my ICE table drawn up. So we've got 1.2 moles initially of nitrogen, 3.6 moles initially of hydrogen. We won't have any ammonia initially because we're assuming the reaction hasn't happened yet. And then we're told that at equilibrium the mixture contains 0.16 moles of ammonia. The first thing we'll do is just look at the change in the ammonia. So it started at 0 and it's got to 0.16. So that's increased. So I tend to just put a little plus sign there. That's gone up by 0.16 moles. So the nitrogen is going to drop by half of that amount because of the 2-to-1 ratio between them. So I'll just go minus 0.08. That's half of 0.16. The ammonia is also going to drop, but it's going to drop by 3/2 times that 0.16. So that means there's a drop of 0.24 moles for that. The other way you could have thought about that is, you know now that this has gone down by 0.08, that's going to go down by 3 times that amount because of that 1-to-3 ratio. So that means at equilibrium, we've got 1.12 moles of nitrogen because it started at 1.2, it's gone down by that much. So there's that much left at equilibrium and there's that much left of the hydrogen at equilibrium. Now the calculation is obviously going to involve the KC expression, so I've written that up there. So remember, that's the equilibrium concentration of the product raised to the power that it's balanced with. So it's balanced with a 2, so it's squared, divided by the product of the equilibrium concentrations of the reactants. So the thing to focus on now is these are moles still, but we need concentrations in the calculation. Now we were given the volume of the container, so it's 8 decimeters cubed. So our equilibrium concentrations are going to be these moles divided by that volume. So there's the equilibrium concentrations there. All we need to do now is put them into the KC expression. So that's coming out at a numerical value of 0.0386. And the last thing we've got to do is work out the units for that KC value. So all I'm doing is putting the units of concentration into the expression. So we've got moles per decimeter cubed squared on the top, because that's what we've got there. And we've got 4 lots of moles per decimeter cubed on the bottom. So we can cancel down. So these will go entirely, and that will go down to 2. So we've got 1 over moles per decimeter cubed squared. So we just bring everything up to the top. So moles squared on the bottom becomes moles to the minus 2. dm to the minus 6 on the bottom becomes dm to the 6.